Okay, so then under acidic conditions, your electrophile is going to get activated. So in this case, the oxygen is going to pick up a proton, and then the nucleophile is going to attack the carbonyl carbon, which causes these electrons to flip up. And then at this point, there's going to be a proton transfer, so the leaving group is going to grab this hydrogen, and these electrons go back to the nucleophile. And then a pair of electrons on this oxygen is going to flip back down, and this kicks off your leaving group. And then because there's a positive charge on this oxygen, you need a deprotonation step. So something is going to come and grab this hydrogen, and these electrons go back to this oxygen. And then in your final product, you have a leaving group with hydrogen on it, and the nucleophile has replaced the leaving group on your acyl function. So these 5 steps, protonation, nucleophilic, acyl, attack, proton transfer, elimination, and deprotonation, probably look familiar. And this is because they are the same steps as for the Fischer esterification, which you probably learned earlier in the semester. And knowing these steps is definitely going to help you with reaction mechanisms, so it's worthwhile to memorize them. And remember for acidic conditions that you need to use equilibrium arrows because all of these steps are reversible. So as an example, we're going to react ethanoyl bromide with water under acidic conditions. And again, you can pause the video and try to work out the mechanism yourself, but I'm going to go through it now. So the oxygen picks up this proton, and then the water attacks, causing these electrons to flip up. So this is your intermediate. And then you're going to have your proton transfer step. So the bromine is going to pick up this hydrogen, and these electrons are going to go back here. And then these electrons are going to flip back down, which kicks off your leaving group. And then in your final product, you have a carboxylic acid and hydrobromic acid.